Linear approximations and differentials. Let's take a look at the following graph. Here we have the graph of a function and the tangent line at the point A, f of A. The linear function whose graph is this tangent line is often called L of x and is the linearization of the function f at the number a. And if you'll notice, if you're close to a, the function and the tangent line are very close to each other. And you can see that as we zoom in here, there's very little distance between these two graphs when you get close to a. Now, as we move farther away from a, the function and the tangent line have a more pronounced difference. But close to a, we can say that the function is approximately equal to the tangent line. And this tangent line, or this linearization, is often referred to as the linear approximation of f at a, or it's sometimes called the tangent line approximation of f at a. Before we move on, let's go ahead and verify this formula for L of x. Because when you think of a tangent line, you probably don't think of this formula. So let's remember how we find the equation of a line. We know that we can use the point slope formula for a line. And we know in this case, the x value here, x1, is actually equal to a. And the y value, y1, is of course equal to f of a. And so this formula becomes y minus f of a equals slope times x minus a. But then we also know that the slope is the derivative of the function evaluated at x1. But again, x1 is equal to a, so we can write this as f prime of a. So we have y minus f of a is equal to f prime of a times x minus a. And if we add f of a to both sides, this formula becomes y equals f of a plus f prime of a times x minus a. And this is the equation of the tangent line written using this notation. And then instead of calling it y equals, we simply replace that with L of x, where L represents the linear approximation. So now we know where these formulas come from. Let's find the linearization L of x of the function at a, given the function f of x equals x cubed minus x squared plus 3, and the number a equals negative 2. So keep in mind that this is nothing more than finding the equation of a tangent line. However, I am going to use the new notation. So L of x is equal to f of a plus f prime of a times x minus a. And so we can rewrite this now as L of x is equal to f of negative 2 plus f prime of negative 2 multiplied by x minus negative 2. And so we only have to figure out what is f of negative 2 and what is f prime of negative 2. Well, for f of negative 2, we only need to plug in negative 2 into the original function. And if we do the calculations on this, we get negative 8 minus positive 4 plus 3, and this is equal to negative 9. Now to get f prime of negative 2, we first need to get f prime of x. And f prime of x is 3x squared minus 2x. And so now f prime of negative 2 is 3 times negative 2 squared minus 2 times negative 2. And this is 3 times 4 plus 4, which is 12 plus 4, or 16. And so the linearization for this function at this point is going to be f of negative 2, which is negative 9, plus f prime of negative 2, which is 16, multiplied by x minus negative 2, which we can rewrite as x plus 2. And this is negative 9 plus 16x plus 32. And if we simplify this, we get 16x plus 23. And here is a graph for reference. So the original function is here. Here we have the tangent line at the point negative 2, negative 9. And if we zoom in, you'll notice that the tangent line and the function are very close to each other when you are near this point. And so this tangent line gives us a way to approximate the function near this point. In our next example, we will use this idea to approximate a function value. Here we want to approximate the natural log of 1.05 using the linearization of the function f of x equals natural log of x at a equals 1. Now, why are we choosing a equals 1? Because 1.05 is very close to 1. So let's go ahead and go through the steps here. We have f of x is equal to the natural log of x. Let's go ahead and find the derivative f prime of x, which is 1 over x. And we know that our linear approximation L of x is f of a plus f prime of a multiplied by x minus a. And in this case, we have f of 1 plus f prime of 1 times x minus 1. And f of 1 is the natural log of 1, which we know is 0. And f prime of 1 is 1 over 1, which is equal to 1. So I'm just plugging 1 into each of these. And now when we replace these values over here, the function value at 1 is 0. The derivative at 1 is 1. And then times x minus 1. And if you do the math on this, you have x minus 1. So this is our linear approximation to the natural log. So now, if I want to do the natural log of 1.05, we recognize that this is the function value at 1.05. And this is approximately equal to the linearization of that same value, 1.05. So in other words, to find the function value at 1.05, I don't have to plug 1.05 into the function natural log. I can instead plug the value 1.05 into the linear approximation. And when I plug 1.05 in here, I get 1.05 minus 1, which is equal to 0.05. And this is our approximation to the natural log of 1.05. And to show you how accurate this is, let's go ahead and take a look at the calculated value. So here you can see on a calculator the natural log of 1.05 is the value 0.04879, etc. Well, to 2 decimal places, this would round to 0.05. And I want you to notice that this is what we got here, 0.05. So this is a very simple way to get a reasonable approximation to a function that you would not otherwise be able to approximate. Now let's talk about the concept of differentials. So the ideas behind linear approximations are sometimes formulated in the terminology and notation of differentials. So if we have a function y equals f of x, where f is a differentiable function, then the differential dx is an independent variable. That is, dx can be given the value of any real number. The differential dy is then defined in terms of dx by the equation dy equals f prime of x dx. So dy is a dependent variable. It depends on the values of x and dx. If dx is given a specific value and x is taken to be some specific number in the domain of f, then the numerical value of dy is determined. Now, before we move on, I think it's very important to understand what's going on here. So here again we have a function f of x, and we have the tangent line drawn to that function. This time we're saying it's being drawn at some number x. Now we know that near this number, the tangent line is very close to the function. Now, as you start to move away from this number, you'll notice that the function and the tangent line are a little bit different. So when we move from x to a value close by to x, which we're calling x plus delta x, where this distance from here to here is understood to be delta x, delta y is the change in the y value. So at x, the y value was here. When you move over to this x value, now the y value is up here. So the y value changed from this value to this value. And that measured change is what we call delta y. Now on the tangent line, if we move from x to this new x value, you'll notice that the y value is up here. Okay, this distance, the distance from the original point to the new point on the tangent line, is what we call dy. And the idea is dy and delta y are approximately equal to each other, but only if we are near this point. So for example, if you look at delta y right here, this distance is not really the same as this distance. They're pretty far apart from each other. But if we move closer to x, so let's say we were right here, this distance, delta y, is now much closer to this distance, dy. And so the idea here is dy is approximately the same as delta y. Now, how do we calculate dy? Well, it's actually pretty simple. The way to calculate dy is to first think about the tangent line and the fact that when you move from one point on the tangent line to another point on the tangent line, the slope is involved in that calculation. So we know the slope of the tangent line is equal to the change in y, which is dy, divided by the change in x, which is delta x or dx. But we also know that the slope of the tangent line is f prime of x. So if we say f prime of x is equal to dy dx, then if you multiply both sides by dx, like so, the dx's cancel out, and you can solve for dy as f prime of x times dx. And this is how we can calculate the differential dy. And that is precisely what was stated here. Now, the truth is, you just need to know that this is true. But this is the reason why. Let's take a look at an example. So here we are asked to find the differential of the function. and we have a function y equals the square root of 1 minus t to the fourth. So if I think of that function as f of t, I can rewrite it as 1 minus t to the fourth to the 1/2 power. And we know the differential dy is going to be f prime of t times dt, right? That was the formula on the previous page, but here our independent variable is t instead of x. So I'm just putting a t in here instead of x. So to get the differential, we need the derivative. So f prime of t is 1/2 times 1 minus t to the fourth to the negative 1/2 multiplied by negative 4t to the third. And this, of course, is the chain rule. Now, if we put all these things together, this derivative can be expressed as negative 4t to the third divided by the 1/2 here, puts a 2 in the denominator, and then 1 minus t to the fourth becomes a positive 1/2 power. And so to finalize this, f prime of t is negative 2t cubed divided by the square root of 1 minus t to the fourth. And here all I did was say 2 goes into 4 2 times, and then I changed the 1/2 power into an exponent. So back to our differential, dy is going to be f prime of t, which is this expression. So negative 2t to the third divided by the square root of 1 minus t to the fourth times dt. In our next example, here we want to find the differential dy and evaluate dy for the given values of x and dx. So here we have our function. So let's write down f of x equals cosine of pi x. And we want to find our differential, which is dy equals f prime of x times dx. So let's go ahead and find the derivative. The derivative of cosine of pi x is negative sine of pi x multiplied by the derivative of pi x, which of course is just pi. And so our derivative simplifies into negative pi sine of pi x. So now for part A, our differential dy will be f prime of x, which is negative pi sine of pi x times dx. So this is the answer to the first part. And now for the second part, we are only asked to evaluate this for this given value of x to be 1/3 and dx to be negative 0.02. And so dy here will be negative pi sine of pi times 1/3 times negative 0.02. And in this case here, I think it's important to put parentheses here and also to put parentheses here. And in fact, I'm going to rewrite this as negative, negative. So the negative here and the negative here cancel, which give us positive pi times 0.02 and then sine of pi over 3. And this is pi times 0.02 times the sine of pi over 3 is the square root of 3 over 2. And then we would approximate this, or you could get an exact value. In fact, let's go ahead and give the exact value here. So this would be pi times 0.02 is 2 over 100, and then radical 3 over 2. And then you could cancel the 2's here, and you could write this as pi radical 3 over 100. So this would be the exact value of dy. And then you could also plug it into a calculator to get a decimal approximation. And that approximation is 0.0544139, etc. So we could say this is about 0.054 if I cut that off to 3 decimal places. In the next example, we are going to use a linear approximation or differentials to estimate the given number. And so we have the square root of 100.5. So first of all, we need to identify a function that we could use to approximate this. And I think it's fairly obvious that the function we need to use is the square root of x, since f of 100.5 would then be the square root of 100.5. But the problem is we don't know how to take the square root of 100.5. So let's go ahead and use a linear approximation. So we know that L of x is equal to f of a plus f prime of a times x minus a. And then we need to pick our a value. Now your a value has to satisfy two things. First of all, it has to be close to this number. And again, close is one of those words that is not precisely defined, but it needs to be close to here. And we should also pick a number that we know how to take the square root of. So the obvious choice here would be to pick a equals 100, since 100 is very close to 100.5, and we also know the square root of 100. So our linear approximation is going to be f of 100 plus f prime of 100 times x minus 100. And now we just need to do these calculations. And so first of all, we know that f prime of x is 1 over 2 times the square root of x. And I'm actually going to remind you where that comes from. So square root of x, you know, is x to the 1/2. So when you take the derivative, it becomes 1/2 x to the negative 1/2, which becomes 1/2 times 1 over x to the 1/2, which becomes 1 over 2 times x to the 1/2, which is 1 over 2 times the square root of x. Now you should memorize this derivative because it comes up all the time, and so it is good to know that the derivative of radical x is simply this. So now let's go ahead and find our function value, f of 100. That is going to be the square root of 100, which of course is 10. And then f prime of 100 will be 1 divided by 2 times the square root of 100, which is 1 divided by 2 times 10, which is 1 divided by 20. And so now our linear approximation will be f of 100, which is 10, plus f prime of 100, which is 1 over 20, times x minus 100. And if we simplify here, we have 10 plus 1 over 20 times x minus, and then 1 over 20 times 100 is 5. And so our final simplification here, we have 1/20 times x plus 5. And this is the linear approximation to the square root function at 100. But remember, they wanted us to approximate the square root of 100.5. Well, the square root of 100.5 is the function value, f of 100.5. But we know that this is approximately equal to the linear approximation at that same number, 100.5. And this we can plug into L of x, and it will give us 1/20 times 100.5 plus 5. Now, you could use a calculator to do this, but the point here is that you could also do this by just doing division. So 100.5 divided by 20. 20 goes into 105 times. Put the decimal point here. 20 does not go into 5, so we put a 0, and then we bring a 0 down. 20 goes into 52 times. Multiply. And then 20 goes into 105 times. And so 1/20 times 100.5 is 5.025, and then plus 5. and this is 10.025. And this is approximately equal to the square root of 100.5. And once again, if you plug in the square root of 100.5 on a calculator, you will see that if we round this to 3 decimal places, we would get 10.0249, but that 9 rounds this 4 up to a 5. So this is a very good approximation for something that we can do in our head, right? We don't need a calculator to do what we did here. The next example is just like the last one. Use a linear approximation or differentials to estimate, in this case, the cosine of 29 degrees. So let's go ahead and define our function. F of x is going to be the cosine of x, of course. Let's do the derivative. F prime of x will be negative sine of x. And we are taking f of 29 degrees, which would give us the cosine of 29 degrees. Okay, first and foremost, we do not use degrees in calculus. So what we need to do is figure out how many radians is 29 degrees. So to get the radians, we're going to multiply by the conversion factor, pi over 180. And this gives us 29 pi over 180. And that actually does not simplify. So the cosine of 29 degrees is equal to the cosine of 29 pi over 180 radians. And that, of course, is f of 29 pi over 180. And we're going to approximate this by getting the linear approximation and plugging in that same number. So it all comes down to, once again, finding L of x, which is f of a plus f prime of a times x minus a. And we need to make our choice for a. So a needs to be a number that is near 29 degrees and a number that is convenient for us. And I think it is fairly obvious here that a needs to be 30 degrees. However, once again, a cannot be in degrees, it must be in radians, so we need to remember that 30 degrees is the same as pi over 6. So now we're going to find f of pi over 6, f prime of pi over 6. That will be cosine of pi over 6, which is radical 3 over 2, and the sine of pi over 6, negative sine of pi over 6, which is negative 1/2. And so our linear approximation, which of course is f of pi over 6 plus f prime of pi over 6 times x minus pi over 6, is going to be radical 3 over 2 plus negative 1/2 times x minus pi over 6. If we multiply this out, we get radical 3 over 2 minus 1/2 times x plus pi over 12. So here I'm just multiplying. Negative 1 times negative pi is pi, and 2 times 6 is 12. And so our final linear approximation here is negative 1/2 x plus pi over 12 plus radical 3 over 2. Now, if I want the cosine of 29 degrees, we know that that's the cosine of 29 pi over 180, which we know is f of 29 pi over 180, and that is going to be approximately equal to L of 29 pi over 180. And L of this is negative 1/2 times 29 pi over 180 plus pi over 12 plus radical 3 over 2. And for this, you really do need a calculator. So let's go ahead and calculate this. And so we can see that this value is approximately 0.875. Get that right here. And then I also plugged in the cosine of 29 pi over 180. And you can see that that is also 0.875. So again, I'm just verifying that this approximation is actually correct. For our final example, we will use differentials to approximate error. So here it says the radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. So you need to understand that when things are measured in the real world, there is a margin of error of that measurement. Nothing can be measured precisely. So here we are saying that we have a circular disc, so just think of a circle, and that has a radius r, and r has been measured to be 24 centimeters. But the error in that measurement is 0.2 centimeters. Now the error in that measurement is what we call delta r or dr. So we're going to think of it as dr. So this is the information that has been given. Now we want to use differentials to estimate the maximum error in the calculated area of the disk. So when we go to talk about area, first thing we need is the area of a circle. And we know that area is pi times r squared. And so dA, which would be the error in the area, we can calculate that by doing the derivative, which is 2 pi r multiplied by dr. So here I'm just using the idea that dA is equal to f prime of r times dr. Okay, so if we regard pi r squared as our f of r, f prime of r is just 2 times pi times r. So then dA would be equal to 2 pi times the measured value of r, which is 24 centimeters, times dr, which is 0.2 centimeters. And then we just need to calculate this. And this is approximately 30.159. And this will be square centimeters because we have centimeters multiplied by centimeters. So what this means is that if your measurement of r is off by 0.2 centimeters, your calculated value for your area could be off by as much as 30.159 square centimeters. So if your measurement of r is wrong, the measurement of your area is also wrong. And this tells us how much it might be wrong by. Now for the second part, we're going to find what's called the relative error of the measurement of A. And then finally, the percentage error. So the relative error is very simple. The relative error is going to be the calculated value of the error. And so that's dA in this case, right? Because dA was the error in A. And then you have to compare that to the value of A. So the relative of error in anything is d that thing divided by that thing. Now, we're going to plug in the formulas for these. So dA is 2 pi r times dr, and A is pi r squared. And notice that we can simplify this. The pi's cancel out. This r cancels out one of these r's, and we end up getting 2 times dr divided by r. And now I can just plug in these values. So dr was 0.2 centimeters, and r was 24 centimeters. And when you do the relative error, the units should always cancel out. So the centimeters cancel out here, and we get 2 times 0.2, which is 0.4, divided by 24. And then we want to simplify this. What you can do here is you can actually multiply the top and bottom by 10. And so that gives us 4 divided by 240, and this simplifies to 1 over 60. So the relative error is 1 over 60. So what that means is that if your radius is off by this much, your calculated value for your area will be off by 1/60th the value of the area. And then the final thing is they want the percentage error. Now the percentage error is very simple. Your percentage error is basically just this value, but expressed as a percent. And if you convert 1 over 60 to a percent, you get 1.667% approximately. So your relative error and your percentage error are really the same thing. It's just that one is expressed as a fraction and the other is expressed as a percent. And that concludes this video lesson.